Welcome to the interactive chemistry quiz, Action and Reaction in Chemistry. I am Noureddine HALI, Associate Professor, and this session brings together several core areas of chemistry. We'll explore molecular geometry, the cohesion of matter, structures of organic entities, organic syntheses, and combustion reactions. Each section is designed to test understanding and connect key ideas across these topics. The goal is not only to choose an answer, but to think chemically and understand why that answer makes sense. This slide introduces the topic of molecular geometry, the central theme for this section. The title signals that the focus will be on how molecules are arranged in space and how that arrangement can be represented or understood. The slide is intentionally minimal, with the theme label and section number providing context without adding visual detail. As we move forward, I'll use this topic as the foundation for interpreting the material that follows. The question asks us to identify the shape and polarity of the ammonia molecule, NH3. The correct answer is polar and pyramidal in shape. Its three NH bonds form a triangular base, while the lone pair on nitrogen pushes those bonds downward, creating a trigonal pyramidal geometry. Because nitrogen attracts electrons more strongly than hydrogen, and the molecule is asymmetric, the bond dipoles do not cancel. NH3 therefore has a permanent dipole moment. A fascinating detail is that ammonia can undergo quantum inversion, with the nitrogen moving through the hydrogen plane at an extremely high frequency. The correct answer is that the ammonium ion NH4+ is nonpolar and tetrahedral in shape. Nitrogen forms four equivalent covalent bonds with hydrogen, producing a symmetrical tetrahedron with bond angles of about 109.5 degrees. Because the charge distribution is so symmetrical, the centers of positive and negative charge coincide, making the ion nonpolar. The cubic and pyramidal options are incorrect. Cubic geometry does not apply to this four-bond arrangement, while pyramidal geometry describes ammonia, NH3, which has a lone pair of electrons. The correct answer is polar and V-shaped or bent geometry. Water's two lone pairs of electrons repel the OH bonds, creating a bond angle of about 104.5 degrees. Because oxygen is much more electronegative than hydrogen, and the molecule is asymmetrical, the charges do not cancel, making H2O highly polar. This polarity allows water molecules to form hydrogen bonds, which help explain why ice is less dense than liquid water and floats. The other choices each contain one error. Water is not nonpolar, and its shape is not called U-shaped. The correct answer is nonpolar, planar, and linear in shape. In carbon dioxide, the carbon atom is centered between two oxygen atoms, creating a straight line geometry with a 180-degree angle. Each carbon-oxygen bond is polar because oxygen attracts electrons more strongly, but the molecule's perfect symmetry causes those bond dipoles to cancel. As a result, the molecule is overall nonpolar. A useful related fact is that, at atmospheric pressure, carbon dioxide transitions directly between solid and gas rather than forming a liquid. The correct answer is polar and planar with a triangular shape. Methanol, or CH2O, has a central carbon bonded to oxygen and two hydrogen atoms with no lone pairs on the carbon. This gives the molecule a trigonal planar arrangement with bond angles close to 120 degrees. It is polar because oxygen strongly attracts electrons in the carbon-oxygen double bond, creating an uneven charge distribution. A square shape would require four bonded atoms, and the molecule cannot be nonpolar because its dipoles do not cancel. Remarkably, methanol has also been detected in deep space. The correct answer is that methanol, CH3OH, is polar and has a distorted tetrahedral arrangement around the carbon with a bent shape around the oxygen. The key distinction is that the molecule bends at the oxygen, not at the carbon. The oxygen's two lone pairs create that band geometry, while the polar OH bond and the uneven distribution of charge make the entire molecule polar. An octahedral non-polar description does not apply here, since octahedral geometry involves 6 bonds, and methanol clearly does not have that structure. The correct answer is trigonal planar or triangular planar, with silicon as the central atom. Silicon forms 2 single bonds with hydrogen and 1 double bond with oxygen, creating 3 bond directions in a single plane with angles close to 120 degrees. Oxygen is a terminal atom, not the center, so the molecule is not three-dimensional or tetrahedral. Salanone is also exceptionally unstable and reactive at room temperature and has mainly been observed under extremely cold conditions or in interstellar space. Well done on analyzing its structure correctly. The correct answer is tetrahedral. The phosphonium ion pH4+ has a central phosphorus atom bonded to 4 hydrogen atoms with no lone pairs on phosphorus. That corresponds to an AX4 arrangement, where the bonds point toward the 4 corners of a tetrahedron, creating angles of about 109.5 degrees. Helical geometry is associated mainly with larger molecules, such as DNA or proteins, while octahedral geometry requires 6 surrounding atoms or electron pairs. So pH4+ is not helical or octahedral, it is tetrahedral. The correct answer is XEF4, or xenon tetrafluoride. Its VSEPR classification is AX4E2, 4 bonding pairs and 2 lone pairs around the central xenon atom. The lone pairs position themselves opposite one another, minimizing repulsion, while the 4 fluorine atoms remain in one plane and form a square. By comparison, SF4 is seesaw-shaped because it has 1 lone pair, and SIF4 is tetrahedral because it has no lone pairs. This is also a historically important molecule, since XEF4 helped prove that noble gases can form stable compounds. The correct answer is KLF chlorine trifluoride. Its central chlorine atom has 3 bonding pairs and 2 lone pairs, giving an AX-E2 arrangement. In VSEPR theory, the lone pairs occupy equatorial positions to reduce repulsion, leaving the fluorine atoms in a slightly distorted T-shaped geometry, with bond angles near 87.5 degrees. By comparison, both NH- and ClO- are AX-E1 species, so they have trigonal pyramidal geometries. One important safety note: KLF is exceptionally reactive and can ignite many materials spontaneously. This slide introduces Theme 2, Cohesion of Matter. The central idea is to consider what holds matter together and gives it unity, rather than viewing it as a collection of unrelated parts. As we move through this theme, I'll use cohesion as the organizing lens, connecting the individual points back to the broader question of how matter maintains structure and continuity. In other words, this section asks us to focus on relationships, connections, and the forces that create a coherent whole. The correct answer is attractive. A calcium ion, Ca2+, has a positive charge, while a chloride ion, Cl- has a negative charge. Under Coulomb's law, opposite charges attract, creating the strong electrostatic interaction known as an ionic bond. Repulsive would only apply to charges with the same sign, and a van der Waals bond would not accurately describe this interaction. This same attraction also helps calcium chloride draw moisture from the air, which is why it is such a powerful dehydrating agent. The correct answer is hydrogen bonds between water molecules. In solid water, these bonds create a highly ordered three-dimensional network that holds the molecules together. They also force the molecules slightly farther apart, producing an open hexagonal crystal structure. That structure explains an important property of ice. It is less dense than liquid water, so it floats. Van der Waals, forces and other attractive interactions are present, but they are much weaker and are not the main source of cohesion in ice. This question asks which molecule can form hydrogen bonds between molecules H2O, H2 or CH4. The key requirement is that hydrogen must be bonded to a highly electronegative atom, specifically nitrogen, oxygen or fluorine. Water is the correct answer because oxygen attracts the shared electrons strongly, creating the polarity needed for hydrogen bonding. H2 and CH4 do not have hydrogen bonded to one of these atoms, so their bonds are not polarized enough. These interactions are also essential for holding the DNA double helix together. The key idea is that an ionic solid is held together by electrostatic attractions between ions with opposite charges, positively charged cations and negatively charged anions. Opposite charges attract, while charges of the same sign repel. So cation-to-cation interactions are repulsive, and anion-to-anion interactions are also repulsive. Neither contributes to the solid's cohesion. This strong attraction helps explain why ionic crystals, such as table salt, have very high melting points above 800 degrees Celsius. Excellent work if you selected the interaction between cations and anions. The correct answer is Coulomb electrostatic interactions. These long-range forces create mutual attraction between positive ions or cations and negative ions or anions, holding the ionic lattice together. Van der Waals interactions are associated mainly with the cohesion of molecular solids, and they are too weak to maintain an ionic lattice. Hydrogen bonds are also intermolecular forces, but they require hydrogen bonded to a highly electronegative atom such as oxygen, nitrogen, or fluorine. In molten or dissolved salt, mobile ions can conduct electricity, unlike solid salt. Well done! Molecular solids are held together by intermolecular interactions, not by ionic forces between fully charged ions. Van der Waals interactions are present in all molecular solids, while hydrogen bonds provide additional cohesion when polar molecules contain hydrogen bonded to highly electronegative atoms, such as oxygen, nitrogen, or fluorine. By contrast, Coulombic electrostatic interactions between ions like sodium and chloride are characteristic of ionic solids. A fascinating example of van der Waals forces is the gecko, which can cling to smooth glass using microscopic hairs beneath its feet. The correct answer is van der Waals interactions, which are present in all molecular solids. Hydrogen bonds can also contribute, but only when polar molecules contain hydrogen bonded to a highly electronegative element, such as oxygen, nitrogen, or fluorine. Coulomb electrostatic interactions are not the right choice here. They act between real ions carrying net charges like sodium and chloride ions, and are responsible for the cohesion of ionic solids rather than molecular solids. A memorable example of van der Waals forces is how geckos can cling to smooth glass without glue. The correct answer is that van der Waals interactions are weaker than both Coulomb electrostatic interactions and hydrogen bonds. Coulomb interactions involve full charges as in ionic bonds and require much more energy to break. Hydrogen bonds are also stronger intermolecular forces. Van der Waals interactions are individually very weak, but their combined effect can be substantial. In fact, billions of these tiny interactions help a gecko cling to a ceiling with just one toe. So, well done if you selected the first two statements, and remember that saying they are stronger than Coulomb interactions is incorrect. The correct answer is a regular three-dimensional stacking of cations and anions. These oppositely charged ions are held together by electrostatic forces, while their balanced arrangement keeps the solid electrically neutral. That regular lattice is also what gives salt crystals their characteristic cubic shape. A solid made only of anions would be unstable because like charges repel, and when molecules form an ordered structure, as in ice or sugar, the result is a molecular solid, not an ionic one. Well done. The correct conclusion is that the stronger the intermolecular bonds, the higher both the melting point and the boiling point. Strong attractions hold molecules together more tightly, so more thermal energy is needed to separate them during a phase change. That means higher temperatures are required to melt a solid or boil a liquid. The statement that stronger bonds produce a lower melting temperature is incorrect. It's exactly the opposite. Water is a useful example. Hydrogen bonds help keep its boiling point high enough for liquid water to exist under conditions that support life. This slide introduces theme 3, focused on the structures of organic entities. The central idea is structure, how organic entities are organized, arranged, and understood as connected forms rather than isolated parts. At this point, the slide serves as a thematic heading, so it establishes the subject without presenting specific examples or detailed analysis. As we move forward, this theme will provide the framework for examining the organization and defining features of organic entities. The emphasis is on understanding structure as the foundation for interpreting what follows. The correct answers are 1 oxygen atom and 27 carbon atoms. The molecular formula, C27H46O, tells us the exact number of each type of atom. 27 carbon atoms, 46 hydrogen atoms, and 1 oxygen atom. So, the statement claiming 27 hydrogen atoms is incorrect. Remember, the subscript belongs to the chemical symbol immediately before it. Cholesterol is also essential to life, helping form cell membranes and serving as a precursor for vitamin D and important hormones. Excellent work, and keep paying close attention to those subscripts. This slide confirms the correct molecular formula for the glyceraldehyde model, C3H6O3. We can verify it by counting 3 carbon atoms, 6 hydrogen atoms, and 3 oxygen atoms in the model. The molecule is also chiral, meaning it can exist in 2 mirror image forms, much like our left and right hands. When writing the semi-developed formula, remember that the aldehyde group must appear as CHO, or CH equals sign O. This notation respects carbon's 4 covalent bonds and avoids the valence error shown in the other proposals. Excellent work. This slide provides feedback on the molecule shown, whose semi-developed formula is CH3CH2COOH, or propanoic acid. The key concept is the carboxyl group COOH, which combines 2 functional groups, a carbonyl group C equals SAN O and a hydroxyl group OH. That means the choices identifying both groups are correct. The exercise classified is a carboxylic acid as a destructor, even though the molecule is chemically a carboxylic acid. Propanoic acid can also be produced naturally by bacteria and contributes to the odor of sweat. Excellent work. The first and third choices are correct because they contain a carbonyl group defined by a carbon-oxygen double bond, OC equals O. In the first option, that group appears at the end of the chain, making it an aldehyde. In the third, the carbonyl carbon is bonded to 2 other carbons, making it a ketone. The second option is different. Its carbonyl is directly attached to an OH group, forming a carboxyl group characteristic of carboxylic acids. Carbonyl compounds also contribute to familiar aromas, such as vanilla and cinnamon. The correct answers are, has 8 carbon atoms and is an aldehyde. The name octanol gives us both clues. Octa tells us the main chain contains 8 carbon atoms, while the suffix al identifies an aldehyde with a carbonyl group at the end of the chain. It is not an alcohol, because alcohols contain a hydroxyl group, or OH, and usually end in ol, as in octanol. Octanol can occur naturally in citrus oils, where its scent is fruity at low concentration and sharp at high concentration. The correct name for the molecule shown is ethanol, or acetaldehyde. The chain contains 2 carbon atoms, so we use the prefix -ita, and the terminal aldehyde group gives us the suffix -al. It is not methanol, which contains only 1 carbon atom, and 2-methyl-methanol is not a valid IUPAC name. Ethanol is also associated with hangovers because the liver produces it when breaking down ethanol, and it is more toxic than alcohol itself. Well done, and keep up the excellent work. Great job. The correct answer is the third option, 2-methylbutane-1-ol. The key is to choose the longest chain attached to the hydroxyl group. It contains 4 carbon atoms, making the parent chain butane-1-ol, and the methyl group is attached to carbon 2, counting from the carbon bearing the OH group. Option 1 places the methyl group at carbon 3, while option 2 has a main chain of only 3 carbons. The semi-developed formula shown here represents this structure. 2-methylbutane-1-ol is also associated with apple and cocoa aromas. The correct answer is 2,3-dibromobutane. The parent chain contains 4 carbon atoms, so the base name is butane. 2 bromine substituents are attached to carbons 2 and 3, giving the prefix 2,3-dibromo. The alternatives shown do not follow IUPAC naming conventions, because halogens are named as prefixes and the parent alkane comes at the end. One interesting detail is that this molecule can form a mesostereoisomer, which is non-chiral because of its internal symmetry. Excellent work applying the nomenclature rules. The correct answer is Z-manntoth-ionine. The parent chain has 4 carbon atoms with the double bond beginning at carbon 2. Because the 2 higher priority methyl groups are on the same side of the double bond, the configuration is Z, meaning together. This is different from E-manntoth-ionine, where the methyl groups lie on opposite sides, and from methylprop-on-ionine, which is a branched constitutional isomer. Z/E isomerism is also important in human vision, where light triggers an ultra-fast Z to E change in retinal and initiates a nerve signal. Great job. The correct answer is secondary alcohol. In 3-methylbutane-2-ol, the carbon bonded to the hydroxyl group is attached to 2 other carbon atoms, a methyl group and a CH group bearing another methyl group. This classification matters because secondary alcohols can oxidize to ketones. By comparison, primary alcohols oxidize first to aldehydes and then carboxylic acids, while tertiary alcohols generally resist mild oxidation because they have no hydrogen attached to the functional carbon. This slide introduces Theme 4, Organic Synthesis. It marks a transition to a topic focused on the preparation and development of organic compounds through synthesis. The slide itself is intentionally minimal, so the key takeaway is the theme designation and the subject area it represents. As we move forward, I'll use this section to organize the material around organic synthesis and the ideas associated with it. There are no additional figures or supporting details on this slide, making the title the central point. The correct answer is to avoid material losses. During reflux heating, vapors form as the mixture boils, and the water condenser cools those vapors so they return directly to the reaction flask. This lets the mixture boil for an extended time while keeping volatile reactants or products from escaping. Reflux is not used to collect products, that is the purpose of selective distillation. And although the condenser improves safety by limiting vapor emissions, its primary purpose here is to preserve material and support the reaction yield. Excellent understanding of this laboratory technique. The correct answer is filtration. It is used to isolate a solid produced during a synthesis when that solid is suspended in a liquid. With simple gravity filtration, the liquid passes through the filter while the solid remains behind. Vacuum filtration, using a Buchner funnel, speeds up the process and begins drying the solid through airflow. Distillation is for separating liquids with different boiling points, while liquid-liquid extraction separates substances between two immiscible liquid phases, typically with a separatory funnel. So excellent work on identifying the appropriate isolation technique. The correct answer is solubility. Recrystallization takes advantage of how differently the desired compound and its impurities dissolve in a suitable solvent at high and low temperatures. The compound dissolves when the solvent is hot, then forms crystals as the solution cools, while many impurities remain dissolved. Density is relevant to techniques such as decantation or centrifugation, and melting point is useful for checking purity afterward. Neither one is the separation principle here. At the microscopic level, the crystal lattice naturally excludes particles that do not fit its structure. The correct answer is accelerate the chemical reaction. Heating increases the molecule's thermal agitation, leading to more effective collisions and a faster reaction. However, it does not change the final equilibrium state, so heating alone does not increase the maximum yield. It also does not eliminate impurities. That requires purification steps such as filtration, washing, or recrystallization. As a general chemistry rule, a 10 degrees Celsius increase can roughly double reaction speed, which helps explain pressure cooking and why freezing slows food degradation. The correct answer is vacuum filtration using a Buchner funnel. It separates a solid from a liquid efficiently, while suction from a water aspirator or pump speeds up filtration and helps dry the solid. A separatory funnel is not appropriate here. It is designed for two immiscible liquids and could clog if used with a solid. Simple filtration can separate a solid and liquid, but it is slower and leaves the solid less dry. So well done. Vacuum filtration is the preferred laboratory method. To check whether a synthesized solid is pure, the most direct method is to measure its melting point using a Koffler bench. A pure substance melts sharply at its characteristic tabulated temperature. Impurities lower the melting temperature and broaden the melting range. Thin layer chromatography can also reveal impurities, but it is mainly a rapid qualitative check, while density measurements are more useful for liquids. This melting point depression is related to cryometry, the same principle behind spreading salt on roads to lower water's freezing point. Excellent work. To identify and assess a synthesized solid product, the most direct method is to measure its melting temperature. A pure substance melts sharply at its characteristic tabulated temperature, while impurities lower the melting point and broaden the melting range. Thin layer chromatography can also help detect impurities or confirm that only one spot is present, but it is a rapid qualitative check. Measuring pH is not the appropriate choice here, and density is mainly useful for characterizing liquids. This is the same principle behind using salt to prevent ice from forming. The correct diagnosis is that the reflux setup is unsafe because a lifting support is missing beneath the water heater in its raised position. This support allows the heater to be lowered immediately, breaking thermal contact if the reaction begins to roll away. Even after heating is switched off, the water heater stays hot for several minutes. Also, the condenser must never be plugged. The apparatus must remain open at the top to prevent dangerous pressure buildup. Finally, cooling water should enter from the bottom and leave from the top, ensuring the condenser jacket fills completely and cools effectively. The correct answer is the phase where the species is most soluble. This follows the principles of chemical affinity and the partition coefficient. During liquid-liquid extraction, the compound preferentially dissolves in the solvent that interacts with it most favorably. It is important not to assume that this phase is always on top or always on the bottom. The position depends only on solvent density. Diethyl ether, with a density of about 0.71, forms the upper organic phase, while dichloromethane at about 1.33 forms the lower organic phase. During this synthesis, 0.42 moles of product are obtained, compared with a maximum expected amount of 0.60 moles. To calculate the yield, I divide the experimental amount by the maximum amount, 0.42 divided by 0.60, which gives 0.70 or 70%. The values 0.43 and 0.50 come from calculation errors or from assuming a different product amount. A perfect 100% yield is rarely achievable because of experimental losses and side reactions. This is why green chemistry also considers atom economy, or how efficiently reactant atoms become part of the final product. This section focuses on combustion reactions, chemical processes in which a substance reacts with oxygen and releases energy, often as heat and light. The key idea is that combustion involves both reactants and products. The original substances are transformed into new ones when energy is released. As we examine this theme, I'll focus on how these reactions are represented, what conditions allow them to occur, and how their products help us understand the chemistry involved. The combustion of wood in air is possible thanks to oxygen or dioxygen, which acts as the essential oxidizer in the fire triangle. Without it, combustion cannot continue. Water vapor is produced during combustion and can help extinguish a fire, but it is not an oxidizer. Nitrogen makes up most of the air, yet under normal conditions it is inert and cannot sustain burning. One more important detail: wood does not burn directly as a solid. Heat first causes pyrolysis, releasing flammable gases that mix with oxygen and create the visible flame. The correct answer is water, H2O, and carbon dioxide, CO2. During complete combustion, enough oxygen is available to fully oxidize all the hydrogen and carbon in the hydrocarbon. Carbon monoxide, or CO, is not a product of complete combustion. It forms when oxygen is insufficient, and it is both toxic and odorless. One interesting detail is that the water initially leaves as invisible vapor, then condense in cold air, creating the white plume seen from exhaust pipes or aircraft. Excellent work identifying the product of complete combustion. The correct answer is 3 moles of CO2. The balanced combustion equation is C3H8 plus 5O2, producing 3 CO2 and 4 H2O. Since one propane molecule contains 3 carbon atoms, all 3 must appear in the carbon dioxide products. 1 mole of CO2 would not conserve the carbon atoms, while 4 moles refers to water, not carbon dioxide. A useful reminder is that burning 1 kilogram of propane produces nearly 3 kilograms of CO2, because oxygen from the surrounding air becomes part of the emitted gas. The correct answer is that combustion is incomplete when the oxygen, or O2, is deficient. With too little oxygen, the fuel cannot be fully oxidized, so dangerous products such as carbon monoxide, Colorado, or solid carbon may form. Carbon monoxide is especially hazardous because it is colorless, odorless, and binds strongly to hemoglobin, reducing oxygen delivery throughout the body. By contrast, excess oxygen supports complete combustion, which produces carbon dioxide and water. So the key distinction is simple. Insufficient oxygen leads to incomplete combustion and toxic products. The correct choice is A equals 2, B equals 1, and C equals 2. That gives the balanced equation. 2C plus O2 produces 2CO. We have 2 carbon atoms and 2 oxygen atoms on both sides, so the law of conservation of matter is respected. The other options fail because either oxygen or carbon is unbalanced. It's also worth noting that carbon monoxide can serve as a fuel and, in industrial blast furnaces, as a reducing agent for transforming iron ore into cast iron. Well done. The correct equation for the complete combustion of butane is 2C4H1 derm plus 13O2 yields 8CO2 plus 10H2O. This balances every atom, 8 carbon atoms, 20 hydrogen atoms, and 26 oxygen atoms on both sides. The other options do not conserve matter, because their hydrogen or oxygen counts are unequal. Well done on mastering this process. As a real-world connection, butane is commonly used in lighters and household gas bottles, and its complete combustion produces the very hot blue flame we recognize. This slide confirms the correct answer for item 4. The complete combustion of 3 moles of butane produces 12 moles of carbon dioxide and 15 moles of water. The balanced equation also shows that the reaction consumes 19.5 moles of oxygen, not 21. These values come directly from the stoichiometric coefficients. Multiplying the equation by 3/2 gives the amounts for 3 moles of butane. Excellent work applying stoichiometric proportions. Remember, because air contains only about 21% oxygen, the actual amount of air required is much greater. The correct answer is that combustion consumes less energy than it releases, and it releases energy as heat and light. Although some energy is needed to break the reactant's bonds and start the reaction, forming the product's new bonds releases even more energy. That makes combustion exothermic. Once a spark initiates the process, the released thermal energy can heat nearby molecules and keep the reaction going, which is why combustion can become self-sustaining. Consuming more energy than it releases would describe an endothermic reaction, the opposite of combustion. Well done, all 3 answers are correct. The energy released during combustion depends on the nature of the fuel, because different molecules have different calorific values. It also depends on the mass of fuel consumed. More fuel means more total energy released. Finally, the oxidizer matters. Using pure oxygen instead of air can produce much hotter flames, because air contains only about 21% oxygen. The key takeaway is that none of these factors should be overlooked when analyzing a combustion energy balance. Excellent work. The correct answer is energy is received or absorbed by the system when a chemical bond breaks. Breaking a bond requires energy to overcome the attraction between atoms. Energy is released later when new, more stable bonds form, such as during combustion with carbon dioxide and water.